Hi all, so today I wanted to give a small but important distinction between two similar looking but differently treated questions. So we're looking at questions involving particles that collide, particles that bound, a particle that bounces off a boundary, such as a particle bouncing off a wall. And I just want to clarify how we deal with the coefficient of restitution in these questions. So let's look at the first case. So I'm going to have an oblique collision between particles. For clarity, I'm going to call this particle 1. I'm going to call this particle 2. So let's put some numbers on this, right? So let's say my particle 1 has initial velocity, something nice, 2I plus 2J meters per second. And my particle 2, so it's going up and to the left, it's going to have a negative I velocity, let's say something like negative I plus J meters per second. And we know that after the particles collide, so they're going to collide, and the way we're kind of taught to think about this is as if there's a vertical boundary between these two things here. Our J components are going to stay the same. So over here, I'm going to have some kind of unknown for my I component. That's what I have to figure out. But my J component is going to stay the same. So obviously this P is going to be negative because we're going up and to the left. And similarly, I'm going to have some unknown here for my I component, but my J component is going to stay the same before and after. So here's our kind of before, and here is our after. Right, so let's, for the sake of argument, give ourselves, an E of maybe half, so our coefficient of restitution. And the way we deal with this then is we have our Newton's law of restitution, which is going to be minus E is equal to V1 minus V2, U1 minus U2. So I'm going to have minus a half is equal to P minus Q all over 2 minus minus plus 1. And then I'm going to get an equation like this, P minus Q. And then, of course, to finish out my question, I'd bring in my conservation of momentum, which will lead to simultaneous equations, M1U1 plus M2U2 is equal to M1V1 plus M2V2. And we continue onwards like this. I think most people will be comfortable finishing out a question like this. However, one thing that can be a little bit confusing here is when we deal with the particle bouncing off a wall. So say I have a particle bouncing off a wall and I have, let's say, the same velocity as particle 1. So I'm going to have the same initial velocity, 2I plus 2J. And what we're taught to deal with here is that my rebound velocity, okay, so V or, well, my J component is going to stay the same when I hit a vertical boundary. So that's going to be plus 2J. But my I component is going to be minus E times the initial part of my I component, like this. And say I have the same velocity here, so E is equal to a half in this case as well. Well, I'm going to have minus a half times 2. I'm going to have minus E, minus I, of course, minus I plus 2J. And the difficulty that I see sometimes people run into is applying this logic of only applying my coefficient of restitution to the I component, in this case over here, when we have oblique collisions between particles. You might be tempted to think, well, my particle 1 is going up, hitting something and bouncing over here, so maybe I have to just multiply this component over here by E to get this component here. But in fact, we know that this relationship between the initial velocities and final velocities is a little bit more complicated. It's given by our Newton's law of restitution. And we can actually see this if we look at our case over here on the right. If we were to think about this, if we were to think about the wall as having an initial and final velocity of 0, maybe a strange thing to think about, but what we'd have then is our Newton's law of restitution, V1 minus V2 all over U1 minus U2. But think about V2 and U2 as being 0. So kind of the wall is my second velocities that I'm thinking about here. What am I going to have? I'm going to have minus a half is equal to my initial and final velocities of just the particle that I care about. And what am I going to get here? I'm going to get minus a half U1 is equal to V1. But this relationship here is what I introduced over here. That is how I ended up with my minus I component here for I. So just be careful dealing with these two similar looking but differently treated scenarios when we're dealing with collisions, particle collisions. Thanks for watching.